There we go. Yeah, so there's another homework assignment for you to work on for Tuesday. It's about supremums and infimums of sets. Some of the upper and lower bound theory that we did on the last couple of classes. It will not cover the stuff we're going to be doing today so much. So we're actually already looking at chapter 3 today. But that homework for Tuesday is going to be involving still some of the chapter 2 material. So that's kind of what's coming up. 2 weeks from today is our midterm. I did publish a resources folder. The midterm is going to cover all of chapters 1 and 2, as well as the first couple of sections of chapter 3, which we're going to be done with probably by next Tuesday. So we'll be done well in advance of the exam with the material for that. So I probably will schedule some kind of review session at some point, and I'll record it and post videos for that and all that. I'll let you know. I haven't thought about when I can do it yet. It obviously won't be on a Tuesday or a Thursday because I've got classes pretty much all day on those days. But as we get a little closer, I'll try to find a good time to set up a study session for us. Optional, of course, for anybody who would like to attend it. Just want to remind everybody to keep jumping into my office hours if you've got questions. You can come in Zoom, you can come in person. I was trying to figure out why I wasn't in a great mood last night. I went out to dinner with a friend and says, "You don't seem very happy." And I was trying to think, well, why am I not happy? And then I remembered, oh yeah, I graded these homeworks yesterday. I think the average on this most recent homework assignment was only like 62%. So very low, much compared to say the first 3 homeworks. So something happened, I don't know. I think one thing was that all those problems about proving countable sets and stuff like that, about countable and uncountable sets, they were best done using that big theorem, right? The union of a countable union of countable sets is countable, right? And that is really the best way to do that. A lot of people were getting kind of stuck in the weeds of trying to make bijections in cases where it was actually pretty difficult to do it. So that I would just really encourage you to review the solutions. I did post the answers to, or at least my answers to those homework problems. And also the other thing that kind of caught my eye was that I had sent out an email. Admittedly, it was kind of maybe later than it should have been, but over the weekend, I kind of sent out some hints on a bunch of those homework problems. A lot of people were not using those hints. And there can be more than one way to do a problem, and that's fine. But generally, I'm trying to give people hints that I think will be the easiest way to do things. And some of those problems were really easy if you just sort of use my hints. So check the solutions. You'll see kind of how those hints play out. But I guess the other thing is just make sure you're checking your Canvas email, because I felt like maybe some people just didn't see the hints ahead of time because they were trying to prove the problems much more complicated than they really needed to be. So anyway, just something to keep in mind, guys. Yeah, this class does take a lot of effort and time on task to really get the stuff down. So keep working hard. I'm obviously working hard too. I'll have lots of availability over these next 2 weeks as you're getting ready for your exam. So okay, so with that in mind, I'm gonna go ahead and jump in here. This is just a recap on the board. Some things we did on Tuesday. We talked about, well, I put the Archimedean principle back up here because we're gonna use it like a bunch of times today. So just to remind you what that says, if you have 2 numbers and one of them's positive, then you can always find a natural number n such that n multiples of x is greater than any other fixed number that you have. So y could be anything, it's just some fixed value. You can make n times x greater than y by just choosing an n that's large enough. The Archimedean principle doesn't tell you what n is, but it says that it exists, right? And so we proved that using the whole theory of supremums and infimums and some of that stuff that we had done just prior to that. So very nice, useful result, the Archimedean principle. Just want to have that on the board so we can be referring to it today a little bit. And then just at the end of class on Tuesday, I started talking about sequences, which is what chapter 3 is about. And one of the first things we're going to get into here is convergence of sequences. And for the purposes of that, I have to talk about neighborhoods. So I just, this is already in your notes. This is just the definition of a neighborhood again. if I have some x in the real numbers and I create some radius epsilon, epsilon is this positive real number, then I can make an interval that is centered on x that goes from x minus epsilon to x plus epsilon. It is an open interval, and it is called a neighborhood. Okay, so this is a neighborhood centered at x, and it has a radius of epsilon, right? And yeah, it's literally just an interval. We can write it using the absolute value if we want. It's all the points that are an absolute value of less than epsilon away from x. So that's it. Just the definition of a neighborhood, and this is like three different ways of thinking about it. And then this is kind of this would be the, I guess you could say this is the picture of it. It's just this open interval right here, right? It's just that open interval. Shade that in right there. So that's what the neighborhood would be. And we're going to have lots of conversations about neighborhoods as we're discussing convergence of sequences. It turns out that a lot of calculus concepts can be characterized in terms of convergence of sequences. So this is not just some side topic that's not related to where we're going. This is actually very related to where we're going. And so that's why we're going to spend a little time in this chapter talking about it. Okay, so far so good. Just kind of getting our selves oriented again here. And so yeah, I actually did have just enough time. I didn't have time to do anything with it, but on Tuesday I did have time to write down the definition. What does it mean if xn converges to x? That just means by definition, and that this is a bit of a logic puzzle here. We have to kind of learn this one well. Every word has to be in the right place and in the right order. But it says for every neighborhood of x, so I'm calling the neighborhood U, for all neighborhoods around x, there exists a natural number n naught. So n naught is a natural number such that if n is greater than or equal to n naught, then all of those terms of your sequence, the xn's that have n greater than or equal to n naught, have to be inside of your neighborhood. Okay, so if you make a neighborhood in advance, and then you look at your sequence eventually has to get inside and stay inside that neighborhood. And then if somebody comes along and changes the neighborhood and says, I'm going to make the neighborhood even smaller, you still have to be able to find this n naught. It might be a different n naught, such that from that point on, all of the terms of the sequence are within that neighborhood. So it's like a game that you're playing. It's like a two-person game. One person hands you the neighborhood. The other player has to come up with the n naught. And the person giving out the neighborhoods can change their neighborhood as many times as they want, right? Because it's for every neighborhood. So the player one can change their neighborhood as many times as they want, but then player two always has the option to adjust their n naught. Okay, so if the neighborhood gets smaller, we might have to make n naught larger, right? But as long as player two can always win that game, right? As long as no matter what neighborhood it is, we can always find this n naught, then the sequence converges. xn converges to x. And I think I mentioned this on, so just notationally, I'll just add this here as a bit of notation, and I forgot my tripod, so I'm going to use an eraser to help me with this balancing act here. So xn converges to x can be written in a couple of other ways. Another way of writing it, so this can be written. You can just write it as xn with an arrow pointing to x, and we'll certainly know what that means. Or we can also write it as just the limit as the limit as n goes to infinity of xn is equal to x. Either one of those would be just other ways of writing the same thing. It's just notation for the convergence of a sequence. I will usually, most of the time, I'm going to use this one with the arrow on it. That's kind of the nicest one, I think, to kind of take advantage of there. Okay, what I want to do is I want to rephrase this kind of wordy definition of convergence in the more mathematical notation way, that's the one we're going to use when we're actually doing problems. So I'm going to do that, and I'm actually going to do it somewhere where I won't have to erase it. I think I can just actually erase this right here, because I want to have this up here, because we're going to do several examples. So let's just rephrase. I'm going to put it right here, guys. I'm going to rephrase definition 3.4. And this is literally just, we're not changing the content of the definition. We're just going to write it in a more mathematical notation. Okay? So this is literally, I think the book calls it a proposition, but it's really not. It's really just a rephrasing. So xn converges to x, right? If and only if. And so now I'll give you the characterization. It says for all neighborhoods, well, those neighborhoods are indexed by, let's just do this arrow like this, just the way I've got my board set up here. These are indexed by these epsilons. I'm going to say for all epsilon greater than 0, right? There exists an n naught in the natural numbers, right? Such that if n is greater than or equal to n naught, okay, then xn is an element of U. I can rewrite that as absolute of xn minus x is less than epsilon. So the neighborhood now is being described in terms of that epsilon that essentially tells us the radius of the neighborhood. Okay. So it just means in the long run, for all of the n's that are far enough into the positive realm, all of the terms of your sequence are within epsilon of x. Okay, so for the first few terms, we don't care, right? What happens in the first finitely many terms makes no difference to us. It's really as n goes towards infinity, that's where convergence of the sequence really comes to the forefront, and it is described just in terms of this absolute value inequality now. So with that, I'd like to do a couple examples, unless there's any questions so far. Everybody doing so good? So far, so good? All right, let me go back over here and let's try to, I guess I don't really need this anymore. This is pretty straightforward here. Let me just do my example right here. Just practice a little bit. What I'm going to do here is I'm going to let xn equal 1 over n squared. This would be for any natural number n. And what I'm hoping to do on this example, guys, is I'm going to prove that xn converges. What do you think it converges to, by the way? 0, right? As n gets big, xn is definitely heading towards 0. So that's what we're going to do. We're going to prove it. And I am going to really encourage you to model or write up your proof in the same way that I'm going to do it here. Okay, so this is one where I think it would be best to, not because I'm a stickler about that, it's more just that, you know, I think I've got it tailored down to be as neat and simple as it could possibly be. So let's see if I can do that. So here's the proof. So it's kind of interesting. The first line of this proof, so here's the definition. First line of the proof is always let epsilon greater than 0 be given. So we have our rubber stamp and we just write that down. Let epsilon greater than 0 be given. Now, the heart of these kinds of proofs is to come up with this n naught. But a lot of times you can't just see it immediately from the problem you're looking at, and it takes a little bit of scratch work to figure it out. So the way I like to do this is I actually like to create a little on the side of my proof, not in the middle of my proof, but on the side of my proof, I like to do a little scratch calculation here. This is where I can try my best to figure out what the n naught is. So the n naught is going to have the property that, you know, as long as n is greater than or equal to n naught, absolute of xn minus x should be less than epsilon. So let's just write this down, absolute xn minus x less than epsilon. And I'm going to use logical connectives here, these if and only if arrows in my scratch word. Okay, the first step I'm going to do is I'm just going to replace what everything is. We have 1 over n squared and then minus 0, because the x value here is 0, less than epsilon. Okay, now obviously I don't need the absolute value bars right now because 1 over n squared is already positive. So I'm just going to drop those absolute value bars. That's a safe thing to do. And I'm really trying to solve for n. So one thing I could do is I could flip this inequality over to solve for n. What happens to the inequality when you flip both sides over? It switches, right? It switches direction. So if I flip this over and I want to do n squared, that would actually be greater than 1 over epsilon. Yeah? And again, that is if and only if. This is still on my scratch work. This is not my proof yet. Okay? And then finally, to solve for n here, I would take the square root of both sides. So n would be greater than the square root of 1 over epsilon. Okay. Does that make sense? So now here's what you want to do. You want to choose an n naught that is, first of all, the n naught has to be a natural number. So this square root of 1 over epsilon is probably not a natural number, so let's not go there. But what I can do is I can come back to my good old Archimedean principle, and I can imagine that the y is square root of 1 over epsilon. And I can let x be equal to 1. Okay, so we'll take a look at this AP, guys. If x is equal to 1, then all that this is saying is that there exists a natural number that's greater than whatever you want. So that is now where I'm ready to go back to my proof, and I'm going to say, by the Archimedean principle, there exists, and we're actually calling it n naught right now. There exists an n naught in the natural numbers with n naught greater than square root of 1 over epsilon. So that is just the Archimedean principle. So now I'm in my main proof. If you didn't see the scratch work and you just saw this proof, it would look like this square root of 1 over epsilon was just pulled out of the sky. It's like, how would we have come up with that? And that's totally fine, right? I mean, technically, all that you are required to do is find this n naught. You're not required to show me how you thought up the n naught in the first place, as far as writing up the proof goes. However, by having the scratch work here, I can see how you came up with your square root of 1 over epsilon. Now, what do we actually, we're not done with the proof yet, because once we have produced this n naught, it is up to us to confirm that if n is greater than or equal to n naught, that our inequality down here will be true. That's what the proof requires us to actually show. It's not so much the scratch work, but now the demonstration that this n naught will work. Okay, so let's just check it. We've produced this n naught, but let's just check it. Let's assume that as is part of the definition, that n is greater than or equal to n naught. Then, now do you see that if n is greater than or equal to n naught, and n naught is greater than radical of 1 over epsilon, that we can then say that n itself is greater than radical 1 over epsilon, just putting the two together. It's pretty reasonable, right? So n naught is greater than the square root of 1 over epsilon, and n is even bigger than that. So n would be greater, strictly greater than the square root of 1 over epsilon. And now I have seen the place in my scratch work where we have ended up with our actual proof write-up in black over here, right? We're basically here. And then we can now reverse all these steps, because these are double arrows, right? So if this is true, then so is this, and so is this, and so is this, and so is this. And this is ultimately what you want. So it's pretty much game over at this point. We pretty much have what we want. All we have to say now, and I will allow you to say this as long as I can see your scratch work, I will allow you now in your proof to simply say, rechasing the steps from the scratch in reverse. So if you just add that little phrase or something equivalent to that, retracing the steps from the scratch in reverse, we conclude that the absolute value of 1/n², I'm gonna write -0 here, because 0 is the limit value, is less than epsilon, and that's exactly what you need to prove. Okay, so you, in the scratch work, see, essentially you're working backwards. And I don't want the working backwards to be the way the proof is written. The proof needs to be written forwards. So we do the scratch over here where we're writing things down. This is what we ultimately want to get. So we work backwards till we get to something that allows us to choose our n naught. And then once we've done that, we can come back and start writing the proof forwards. As long as all of your steps are reversible, I don't mind just saying retracing the steps from the scratch. What do you guys think? Is that okay? Let's do another one. Practice another example. I'm going to come over here and do another one. The next one's going to be a little bit more involved, but same idea. So let's do this example. This time, let's let xn equal 2n all over 5n plus 2. And again, n is just a natural number, like always. N is just my natural number. And then I would like to do this. I would like to prove that this sequence xn converges to, what limit do you think this sequence will have when n goes off to infinity?
2.
Yeah, basically both the top and the bottom go to infinity. You might remember L'Hopital's rule, right? Basically you take the derivative of the top, the derivative of the bottom, 2/5, right? It's just going to be 2/. Basically the +2 on the bottom becomes insignificant. As n gets very large, that +2 on the bottom can almost be ignored, which would mean that you're looking at something that's just 2/5. Yeah. We're actually going to probably prove L'Hopital's rule eventually, but of course that involves derivatives. So we technically don't know that yet. I don't mind you using something that you know to kind of figure out what the answer is supposed to be here. It's supposed to be 2/5, but I do want to obviously prove this one now using the definition again. Yeah, okay, great. So we're not proving this with L'Hopital's rule. We're maybe using L'Hopital's rule that we know to think what the answer would be, but then ultimately we're gonna do the proof. Just like we did this one. Okay, so same thing exact, one more time, guys, just gonna do this one more time. Let's let epsilon greater than 0 be given. And then I'm gonna immediately get out my blue marker again and do some scratch work over here. We'll make a column on the right so it doesn't interfere with the proof where we can do our scratch calculation. And in this case, let's see, how does the scratch work look this time? Well, it starts off the same way, absolute xn minus x less than epsilon. End up with. And our job is to solve for this n naught. So let's just replace with if and only if here. I'm just going to replace the xn with what it is, 2n divided by 5n plus 2, and then minus the limit value of 2/5. This is less than epsilon. Okay, so far so good. Okay, so this one is a little harder to solve for n. On this one, we were able to pretty quickly do a simple manipulation. This one will take a little bit more patience. What I would recommend here is that because we are subtracting fractions, I would find a common denominator and turn it into a single fraction. So if I do that, the common denominator on the bottom would be just 5 times 5n plus 2. And then you have to do this sort of cross multiplication thing. 5 times 2n minus 2 times the quantity 5n plus 2. And that's still less than epsilon. So I'm just doing subtraction of fractions here. And this actually can be simplified inside of these absolute value bars. If you look at the numerator, you actually have 10n minus 10n, which cancels. The only thing that survives in the numerator is -4. You see the -4, I have a 2 and a 2. So that's 4, and it's with a minus, but we're taking absolute value. So if we take absolute value, that numerator will just end up being 4, yeah? And then we also don't need the absolute values on the bottom because n is positive, 5 is positive, and 5n plus 2 is positive. So I can get away with just removing those absolute value bars kind of at this point right here. Okay, I actually need to go to another column here. If and only if again. And I want to solve for n. That's really the goal. So what I would maybe recommend that we do is, well, let's just move the 4/5 to the other side. So I'm going to write this as 1 over 5n plus 2 is less than 5/4 of epsilon, right? There's different variations you could do. You could have just flipped the whole thing over right away. So don't let that get you too screwed up because there's many right alterations of this. I'm just giving you one way to do it. Now I'm going to flip everything over. So 5n plus 2 is greater than, it's going to be 4 divided by 5 epsilon. So the 5 epsilon is now on the bottom of that. And now I have to, what, subtract 2 and divide by 5. Can I do this both at the same time? Let's just do one step here. So I'm just going to get n greater than, so what it's going to be is 4 over 5 epsilon minus 2 all over 5. So it's fractions of fractions here. It's a little bit messier than the first example. Maybe some of you don't like that. I can make that into just one fraction, right? I can just put the 5 inside. So I could actually make this as, well, sorry. I'm just gonna put the 5 inside of each fraction separately. So 4 over 25 epsilon minus 2 over 5. Does that sound okay? Yeah, so I think we can do that. So this is the meat. This is the meat of the problem right there. Is coming up with that. Okay. So now can I go back to my proof? Kind of remembering how I did this one and pull out my Archimedean principle. Sound okay? So I'm going to do that by the Archimedean principle. There exists an n naught in the natural numbers with n naught greater than that expression, right? Greater than 4 over 25 epsilon minus 2/5. Yeah. By the way, you don't have to pick the best n naught value, right? So the Archimedean principle doesn't necessarily give you the smallest choice you could have gotten away with for n naught. I mean, guys, if epsilon is pretty big, this is actually going to be a negative number because you're taking some fraction that's pretty small and subtracting 2/5 from it. That could be a negative number, in which case your n naught could just be 1, right? But there's nothing that, and I used to do this that way when I was teaching this class. I'd like try to figure out, well, what's the smallest n naught we could have? And the fact of the matter is we don't have to find the smallest one. We just have to find any n naught. There exists an n naught in the natural numbers. That's exactly what the Archimedean principle provides us. So in this case, we don't have to worry about if this was negative. Sure, we could choose n naught to be equal to 1, but if I choose it to be equal to 3,500, that's also fine. It can be anything. So anyhow, so there's your n naught, and now I'm going to basically just do a rubber stamp on what we did before. Assume that n is greater than or equal to n naught. Okay, so then that means that n itself is greater than 4 over 25 epsilon minus 2/5. And everything in this scratch work was completely reversible. So I'll go ahead and just recopy that same sentence again. I'm going to do this retracing the steps from the scratch. In reverse, we conclude that the absolute value of, what's it gonna be? I'm just gonna put in what we had, which is a 2n over 5n plus 2 minus 2 over 5, that is less than epsilon. Technically, you don't need this first sentence in the scratch, but that's totally okay. The main thing is, I just want you to be careful to not clutter up your main proof with the scratch inside of it. That's where it gets muddled up, and then I have to figure out, well, what's the logic of this? And it's just a little more confusing. So if you could separate that scratch work out, you're going to make yourself understand it a lot more clear. Right, so I think that's the best way to do that. So there's another example, a little bit trickier than the first one, but not too bad. Not too bad. Questions on that? Okay, so I've just done 2 examples of proving that a limit does exist and what its value is using this rephrase definition. There, of course, are going to be sequences that do not converge, which means we're going to flip this definition on its head and say, well, what does it mean for the sequence to not converge? So that means that there exists a bad epsilon for which every n naught fails, right? You cannot find an n naught fails to give you this condition here. So I'd like to show you an example of that as well, but I realize we haven't taken a break yet. And so I would like to give you a short break. Since you took a quiz, you're probably ready to clear your mind for a minute. So let's take a break for about 10 minutes, and then I will do some more examples with this definition. That's the game plan. Okay. How are you doing today, Danny? Are you well? Yeah. Good. Didn't get too wet coming over here today? Did you? Pretty soaking wet. At least you have looks like some quick dry clothes on there. Did they make you guys do this in calculus at all? No. This kind of the epsilon proofs, not in calculus.
We're doing an epsilon delta.
Epsilon delta proof, okay.
That's-
Yeah, and we're gonna come to that later, but
That's all I remember.
not with the sequences, okay, just wondering. I don't think I did this either when I was in school. It
But I
wasn't
also-
until I got to college.
I ended up taking Calc 2 and Calc 3, right? I was in Calc 2 when COVID hit, so it all went online.
Ugh,
I know, we all
Not
tried
a
to
good-
shut it out, but it happened.
not a good time for that.
Sure it was.
Oh, if you say so.
I got to be at home with my kids while they were trying to do online school too.
I see.
So, great times. I was in Calc 3 right before COVID. I took him to join our family. Right. He's great.
I just saw him 30 minutes ago, right before
He's
class.
good.
He stopped in.
So much.
Yeah,
This looks really.
yeah, he does.
He feels really good. I took it at community college. And the professor that I took it with, he was retiring, that was his last semester.
Uh-huh.
And he had already planned this, and then COVID hit the semester
Oh my
before.
gosh. Oh,
And so it was he was like, well, I wasn't gonna stick around, but I might have to, because I don't know if anyone else is ready for this.
right.
And now we're on COVID.
Just between you and me, I think Mr. Arthur probably will retire pretty soon. He's been talking about it a little bit. I mean, I think he might be over 70. I'm not sure.
I mean, if Pagny's still.
He's been here a long
Yeah.
time. Well, Pagny's never gonna, probably he'll be coming in the morning, the same morning that his funeral is. Come in and work, and I don't know, he's a different character.
Really
He's
is.
been here since the 70s. And I'm trying to think who the second most senior member of the department would be. Dr. Agnew would be in the running, Dr. Lee. Probably be one of them. Yeah. I'm probably in the top 5 or
You're up
6.
there.
I'm getting up there. Scary. I feel like I just came here. I still remember my job interview here. But nobody who was on my interview panel is here anymore.
It's always kind of funny when he's like, I was on an interview panel for Dr. Blesser. Yeah, I hired him.
Yeah. I love to take credit for that. That's right.
For him to give me that sticker, probably has another one of these. Dude, he hasn't got that bunch of them. Yeah, I don't know why. He's so random.
I've noticed it's a math thing. I have a section that we're like math shirts on Wednesday.
Well, Dr. Chinose has a maid. So he gave it for Dr. Chinose, should be a shirt. So if there's one, have one now, it's either like, upload maybe to me. Yeah, I know, it's fun.
I don't know.
Girl, I do it all the time.
I don't know about, with the kids.
That's what I was doing this morning when you walked in. Okay, so this is like a view, it's like.
March.
the A minus the C, right? So is that just?
So, since the minus was outside.
So, right, it's like
That'd be
this
45.
minus that, but then this.
Maybe I got it.
So this is the number right there, that's. So I rewrote it as.
They get pretty wet though. Today was the day I needed to bring stuff into my office for my car.
I rewrote it as.
I didn't have a problem. So I actually left something in the car, hoping by the time I have to leave. today,
But you get rid of that one.
Did the paper stuff, the paper. It's actually some clothes, because I was thinking of going hiking.
So I
this
think
week.
this one
I
is
that I
this,
moved
but
my
this
hiking
one
gear back and forth,
Is.
so. Today was not a good day for that. It's supposed to clear off, I think, for the weekend. Yeah. Hopefully.
I don't know, I was so.
Just look on the inside, it's saying A.
They're working,
Mhm.
like, working fixture.
So A, yeah, so we only maintain minus a B, but then the B is contained, in C, so then you're getting rid of the C too. But then you're minus C.
So I'm getting rid of C.
Ah, that's great. So you just focus on.
Because I feel like that's what this one says.
That's scholarship or something.
You guys all had to come because
Yeah,
So
these are.
I'm wondering if I should take bets on how many cheeks my other
But it
classes.
doesn't.
They don't
matter
have
whether
this.
we're on this, doesn't
I'm gonna
matter.
brave the weather to come in.
Yeah.
Because it's supposed to actually be harder. It's already pretty bad and it's supposed to get worse right about when my second class starts. I'm lucky if
Figured it. Figured out like my last class almost 7 PM, which is like the worst time to be out there with these children.
Between 5 and 7, it's supposed to be pretty rugged.
So I'm like, I'm just gonna hang out here and do some office hours.
Get some homework done, yeah. right?
Homework and-
Yeah.
I got no problem driving at midnight.
Yeah. And you're not, are you going home tonight though?
Yeah.
So you've checked out of your place? Yeah.
Yeah, and I was able to hook up with a lady I stayed with last year and
Oh, okay.
she's like, I can't rent anymore
Uh-huh.
on Airbnb because they need a permit from the city of Fullerton to
Oh,
rent on Airbnb. She goes, but my son's out of town. I have an empty room that's there for him.
oh, okay.
She's like, $40 a night, you'll have the rent of the house.
Oh, my gosh.
And I'm like,
Sold.
yeah, she's like, there's 1 week in March.
Uh-huh.
He'll be here visiting. I'm like,
Other than that, wow, that sounds like.
It's better than 200 and something a week that I'm paying.
Oh, yeah, yeah.
And this house is,
It gets pricey. Yeah. Oh, that's great. And it's not too far away,
a little further than this one, but
still, yeah.
But then I
north,
A lot better than San Diego.
10 to 15.
Yeah.
Well, yeah, 10 to 15, depending on what the traffic is.
Traffic, yeah, yeah.
10 minutes by the time I leave.
Yeah, that's not bad at all.
It'll be fun.
Yeah, I can almost bicycle. So I was like, she's who I tried to hook up with before school started, but I put her number wrong in my phone. was like,
That's a problem.
You know what I told my husband?
Oh.
Yep.
I told my husband-
you know, threes and nines, apparently they look the same to me.
Oh, my gosh. Oh, yeah.
You guys thinking the square root of her phone number? Okay.
Oh, yeah.
So when he got home, he was like,
Oh, yeah, I'm stoked on that. That'll,
Yeah, that, cutting down on that commute time, boy, that's a big help.
and I listen to lectures while I'm riding and stuff, but
Yeah, see, that I could not do.
without the visualization.
Yeah, it's hard. Yeah, I would be worried that I would end up thinking about what he was saying to a point where I was not driving carefully. Yeah, so that would be my worry.
It's okay. I ride fast enough. I'll wake up. I have my car right now because of
Yeah,
hauling everything, so.
yeah, for sure.
Told you all my life insurance is accident, so if I die of natural causes, you don't get anything.
Well, let's hopefully not have to call in the insurance.
It's that time, it's that time.
Yeah, I guess.
I figure I did 24 years for Uncle Sam and I live, so I'm already on borrowed time.
Right. I get you. So that's 24 hours you were in the Navy?
24 years.
24 years? Yeah. Oh my gosh, wow.
24
Time
years and
goes like
28
that.
days.
Oh my goodness, wow. That's a big commitment.
Well, I tried to get out at 20. They denied me retiring at 20.
I see.
They said I was necessary. If I could have got out at 20, my daughter could have got her last 2 years at Cal State paid for it.
Oh, that would have been nice, yeah.
So
All right, guys, I think I might get us all gathered back up here again together. I love all of the chit chat and small talk. It's great. I mean, we're not climbing this mountain of real analysis by ourselves, right? We have friends. I hope that you do have sort of a study buddy or one or two people. I know it's harder these days because everybody does everything from home, on a remote and so on, but yeah, it's great if you've got some people that you can bounce ideas off of and, share your homework thoughts and things like that with. So yeah, keep getting to know one another. We will get back to doing some group work probably next week. This week, just because of the quiz, I want to make sure I'm getting the material covered for the midterm. Not going to do it today, but next week we'll try to get you back some practice in groups as well. But I want to take up that issue that I mentioned about what about sequences that don't converge and how we can prove that using basically the negation of this definition. And so I have a very easy example to kind of do that with. So let's go ahead and write it down. So this time I'm going to take the following statement, the sequence. Well, actually, let's just write the sequence down just like I did before. Sorry. So let me just state it the same way. Let xn equal, I'm going to pick something super easy, -1 to the n. Okay. And again, n is just a natural number. So you obviously know what this sequence is. It's just -1, +1, -1, +1, -1, +1 forever. And so it's not like honing in on a single converging limit value, right? Because it bounces back and forth between these 2 points that are pretty far apart when you think about it on the real number line. So this is not going to converge, and let's try to prove that. So let's prove that xn does not converge at all. So I don't even have any x that I can try to prove that it converges to. Okay, well, the way to do this kind of thing is by way of contradiction. So what we're going to do is, by way of contradiction, we're going to assume that xn does converge, and therefore it would have to converge to something. So I'll say it converges to x, and this would just be for some fixed real number x, right? There would have to be a limit to that sequence, and this is a hypothetical limit, which we ultimately are going to find out does not exist. This is going to be a contradiction. So now, unlike the previous examples where we were trying to prove that a sequence converges, here we are assuming that a sequence converges. And these two perspectives these two different points of view are completely going to change the way we have to think about the definition. Right? If we're trying to prove that the sequence converges to X, then we have to take an arbitrary epsilon greater than 0, right? Let epsilon greater than 0 be given and cook up an n naught. But now we are assuming here that the sequence already converges. So what does that mean? That means that for all epsilons, we will already be assuming that there exists this n naught that we have in our hands. And so we can actually pick whatever epsilon value that we want. Because for all epsilon greater than 0, this thing will be true. Because we're assuming that now. So try to be careful with the logic of this, whether you're assuming the convergence or whether you're proving the convergence. Proving the convergence, which is over there, is going to look very different on paper than when we start off with the assumption of convergence to begin with. You see, actually, in a little while, we're gonna have some theorems that will basically be assuming certain things converge and then proving that other things converge. So you'll have both of them in the same proof at the same time. But for right now, we're going to assume that xn converges to x. So maybe I'll just ease myself into this and just say, so by definition, this just means that for all epsilon greater than 0, I'm just going to recopy what's over here, guys. There exists an n naught in the natural numbers such that if n is greater than or equal to n naught, then absolute xn minus x less than epsilon. Okay, so we're really just copying verbatim that definition into the proof. But right now, I actually want to choose a specific epsilon. And this is actually where the tricky part is to figure out what epsilon you should choose. Since I've already done this proof and I have polished my notes, I know what epsilon I'm going to want to use to get my contradiction. And I am going to write it down, pulling it essentially out of the sky. I'm going to choose epsilon to be equal to 1/2. Okay? You can choose any epsilon that you want. It's not guaranteed that every epsilon would work. If you chose epsilon to be 500, well, then you're talking about a neighborhood of radius 500. Obviously, -1 and +1 can both be inside a neighborhood that is that big, and you're not really going to get a contradiction out of it. Right? So you need to pick a sufficiently small neighborhood. If you had tried epsilon equals to 1 and then run through this proof, you would see at some point that it doesn't quite work. And that would be okay because you would then also see how to sort of tweak it so that it does work. So let me write this down and then I think you'll see what I mean. So given this epsilon, then so there exists an n naught. We do not know what n naught is, but there does exist an n naught such that if n is greater than or equal to n naught, then absolute xn minus x is less than 1/2. It's less than 1/2. So I'm putting in 1/2 for my epsilon here. I don't know what n naught is, but the thing I do know is that there will be n's larger than that are both even and odd. Both of those, right? Given this n naught value, whatever it is, we don't know what it is, but this is for all n greater than or equal to n naught that this has to be true. So we can imagine that there's an even value of n, in which case xn would be 1. And we can also imagine that there's an odd value of n, in which case xn would be -1. Right? So let's just write that down. So then absolute of 1 minus x is less than 1/2. And absolute value of -1 minus x is also less than 1/2. Something like that. Right? By the way, and this is not part of the proof, but if you had your little number line over here with -1 and 1 on it, right? You're saying that the distance from x to 1 is less than 1/2. Well, that means it's got to be, here's 0, by the way. It means it's got to be over here. X has to be here. But then the distance from x to -1 is also less than a half. Well, that means it's gotta be over here. Well, X can't be in two places at the same time. These shaded regions do not intersect. So somehow this is gonna be a contradiction. Let's see if we can figure out how it's a contradiction. If you add these to, well, actually, sorry, this one, the second one I'm gonna do a little tweak with. So leave the first one the same. With the second one, I'm just gonna pull out the minus. So there's a -1 that can be factored out of that absolute value. So I'm just gonna do that. And now what I'm literally gonna do is I'm just gonna add these together. Okay, so I'm just gonna add them together here, guys. So hence, absolute 1 minus x plus absolute 1 plus x is less than 1/2 plus 1/2. Well, 1/2 plus 1/2 is 1. And can we do anything with this part right here? This, what's that? Yeah, the triangle inequality. Excellent. That's exactly what I was thinking about. We could use the triangle inequality. So what I could say is, let me just get it exactly right here. I could just say that the absolute value of 1 minus x plus 1 plus x. So let's just say this, by the triangle inequality, that was a result we looked at last week. By the triangle inequality, I can take this is basically the absolute value of, let's just think of this as like u plus v. The absolute value of one thing plus another. Well, that's going to be less than or equal to the absolute value of u plus the absolute value of v. So I get my two separate parts there. I can split that absolute value apart. And now this thing is what we had already written. It's less than 1/2 plus 1/2, which is 1. Okay, you guys with me? The triangle inequality is really this step right here. All right. Well, what is this equal to right here, by the way? 2. 1 minus x plus 1 plus x. That is just 2. So 2 is less than 1. Contradiction. That is a contradiction. Okay, so there you go. There you go. Okay. That makes sense to everybody? You literally just add this up, it's 2. But then you split it apart using the triangle inequality into two things that are each less than 1/2. So it just doesn't, the math just doesn't work out. So you get your contradiction. So proof by contradiction, a really nice way to prove that a sequence does not converge. Yeah. Okay. So we've done a few concrete examples here. Are there any questions so far about any of these? Or doing okay with this? Let's actually prove some results now that are a little more like general results instead of just specific examples. I'm actually going to state a theorem here. This is still just in the first section of chapter 3. The first theorem here, 3.1. And what I want to do here is I want to prove that if a sequence converges, it can only converge to one number. There cannot be two different x's that the sequence could converge to. So if the sequence xn converges, if the sequence converges, then the limit is unique. The limit is unique. So if a sequence converges, its limit has to be unique. What's a good strategy for proving that something is unique in a math class? Suppose that there's 2 of them, right? And you can either get a contradiction or you can prove that the 2 things are actually equal to each other. Yeah, exactly. So I'm gonna do that here, guys. Let's assume here. Let's assume for this proof that xn converges to x, but also that xn converges to y. So I'm gonna do that, and then we will prove, or we will show. We are going to show in this proof that x is equal to y. That's how I would like to do this. And what I'm basically going to do is I'm going to prove that the difference between x and y is 0. And how am I gonna do that? I'm gonna do that by proving that it's actually that difference. I'm gonna prove that the difference between x and y is less than any arbitrary epsilon. So I'm gonna start off to do this. To do this, I'm gonna start off like I so often will be doing. I'm gonna let epsilon greater than 0. And that is an arbitrary epsilon. It could be 0.000001, right? It's a very small value. And I'm gonna try to show that the absolute difference of x minus y is less than epsilon. But if I have an epsilon in my hand that has appeared out of somewhere, our definition of convergence tells us that there will exist an n naught because we have convergence of, right, xn does converge. So there's gonna exist an n naught now, such that blah, blah, blah. Let's write it down, okay? So by definition, there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, then absolute xn minus x is less than anything I want to put here. Now, I know that I put epsilon, I grabbed the epsilon out of the sky. If you have a pencil, you can write epsilon here for the moment. It's going to turn out to not be the right thing to put there. It's a little bit bizarre, but in a minute, I'm going to have to come back and change this epsilon, but I'm going to just play dumb for a minute. Just going to kind of play along with the definition. So the idea here is, all right, there exists an n naught such that if n is greater than or equal to n naught, then absolute xn minus x is less than epsilon. I will have to change that in a moment. So I'll come back and edit my proof. I'm trying to not just show you, I could just show you the polished proof in perfect form. But if I did that, you wouldn't appreciate sort of the whole thought process that goes into how you derive the conclusion here, right? It's actually helpful because we have to solve these problems and it's not always gonna be polished for us right in the beginning. Okay, so let's just play along for a minute. But see, xn also converges to y. And so again, with this same epsilon, I will just say also, there exists an m naught in the natural numbers such that absolute xn minus, such that if, I forgot the if part, if n is greater than or equal to m naught, then absolute xn minus y is also less than epsilon. So I can play this game with both the x and the y, right? We've got these two hypothetical limits for this convergent sequence. And so for each of them separately, I'm coming up with an n naught, and here I'm calling it an m naught. And they may not be the same number. They may not be the same number. But the trick that we are going to do then is we are going to assume that n is greater than or equal to the max of n naught and m naught. The max. So I want to pick n to be greater than both m naught and n naught. Because I want to be able to use both of these two inequalities, right? That's going to be the idea. Okay. So now, what I'm going to do, if n is greater than or equal to both of those, by choosing it to be greater than or equal to the max. By the way, I can always take a max of two numbers. I would not be able to do that if there were infinitely many numbers listed here, but we only have two, so we can just take the bigger of those two and choose n greater than or equal to that. So thus, we know that both of these inequalities is true. So let's actually write that down. Absolute xn minus x is less than epsilon, and absolute value of xn minus y is also less than epsilon. We have both of those. If you choose your n bigger than the max of the two m naughts and n naughts, then both of those inequalities is true. And now what I wanna do. Didn't I say that I was gonna do this proof by taking the absolute value of x minus y and showing that it was less than epsilon? Let's do it now. Let's check that out. Let's do absolute x minus y. And I'm gonna try to convince you that it's less than epsilon. Well, there's this cute little trick that we can do. There's this trick we do where we insert, you're gonna see this a few times this semester, guys. This trick is where you insert an xn by subtracting it and adding it kind of in the middle of that statement. So this is a trick, but it's a trick you'll see a lot, so you'll probably get used to seeing it. The purpose of doing that is that I want to use the triangle inequality now to split this apart into absolute x minus xn plus absolute xn minus y. You with me? So everybody has to just remember this absolute, this triangle inequality, it's just this. I should have written this down before. We did this about a week ago. It was kind of a elementary property of absolute values there. So I'm taking this thing into two parts, guys. The first part here and then the second part here. It's like my u and my v. Okay, so I'm just splitting this apart. But now x minus xn, how far apart is that? It's less than epsilon, right? And xn minus y, that's also less than epsilon. And so unfortunately, I did not end up with epsilon. I ended up with 2 epsilon. So how can I fix that? Go back to here. Remember I told you to do this in pencil? We're gonna go back here and we want to get epsilon over here. So put epsilon over 2 here and epsilon over 2 here. Why do I get to tinker around with that at my free will? It's because the sequence xn converges to x, so for all epsilons. So I can put anything here that I want to, including the given epsilon cut in half. This is exactly what I'm doing. So how else do I have to edit my proof now? Just right here, guys, make sure you divide by 2 on all of these epsilons that we have. And that means also right here. And now we get epsilon. Okay, so how far apart are these two limits of the sequence? They are less than epsilon apart from one another. The difference here is less than epsilon, and epsilon was arbitrary. It could be so tiny, right? So if x and y were different from each other, we could find an epsilon that would give us a contradiction here, right? So anyway, thus x equals y. That's what we wanted to prove. X equals y. Okay. Questions so far?
How do we change from a less than to an equals?
It's epsilon.
This one to this one?
Yeah.
Oh, this is just epsilon over 2 plus epsilon over 2, which is equal to epsilon. So this equal sign connects from here to here. This less than was coming from here to here. So this line is less than this line.
Gotcha.
But this line is actually equal to this line.
So we're saying that the absolute value of x minus y equals epsilon.
No, it's greater than x.
Absolute value of x minus y is equal, less than or equal to, less than, and then equals. It is less than. So if I have,
Okay.
if I have a.
I'm good. I was following it all the way down the left side.
Yeah.
Threw me off.
Oh, yeah. Oh, by the way, guys, this is, you wanna have in your proofs on something like this, you wanna have white space over here. So you start on the left and then you just do a chain down on one side. I love it when my Math 250B students, they will start writing on both sides of the equation, and then they, at the end of like a whole page of calculations, on the bottom of the paper, it says 0 equals 0. And I'm like, is that what you proved? I knew that about when I was born almost. Anyway, so yeah, you got to be a little careful with that. Try not to get into this habit, which a lot of students have, doing two columns and manipulating both sides of them, that just gets kind of confusing. So it's much better to just, start on the left with an equals, and then put equals or whatever, and then just a chain of things going just on the right-hand side only. That's a great way to structure that. Okie dokie. All right, well, we only have a few minutes here. I'm gonna just state another theorem and maybe we'll have a minute to prove a little piece of it, but if not, that's okay. Nothing I'm gonna say here in these last few minutes is gonna be terribly shocking to you. I just want to state the so-called limit theorems, and these will be very familiar to you. This is actually technically in the next section, just the first part of the next section. So I will state this, this is called limit theorems. And you would have at least probably mentioned these or seen these things briefly mentioned somewhere else, but I'm going to do the theorem in full right here. So this is actually theorem 3.2. And what we're gonna do, guys, is we're gonna take two sequences, xn and yn. So let xn and yn be sequences in R. We just have two sequences of real numbers here. And I'm going to assume that xn converges to x and that yn converges to y. So each sequence converges to something. They are both convergent sequences. They both converge. So then this theorem has 4 parts to it. And all of them are pretty natural. If we take the sequence xn plus yn, if you add the two sequences together, no surprise that that would converge to x plus y, right? We would expect that. We would expect that. Okay, so that's one statement. Secondly, if we multiplied the sequences, so if we took xn times yn, we just multiply them term by term, well, the limit of that will just be x times y. So convergence is preserved with addition or multiplication. The book actually puts in a special case of this, which is what if you take a constant times the sequence? So if you take xn and you multiply all of its terms by c, well, that just converges to c times x. And this is just where c is any real number over here. So I'll just put that on the side a little bit. So c is just some real number, doesn't matter. And then finally, there's one more statement, which is that if we wanted to do division, xn divided by yn, so we have two sequences that we would like to divide, then again, nothing surprising here. The limit of that is just going to be x over y. I do need to put a quick little proviso here, provided, we always worry, of course, in math about dividing by 0. So y should be not 0 in this context. And we also would not want y sub n to be 0 either for any value of n. Otherwise, the sequence yn doesn't even make sense. So just basically just making sure that denominators are not ever going to be 0. And that's all you have to really worry about there. Okay. Well, so this would have probably been shown to you before in a calculus class or something, but may or may not have been proven, probably not. Because the proof is going to be using the epsilon and naught definition that we've been using all day today. It turns out that we do need a few tools to be able to prove parts 2, 3, and 4. Part 1, not so much. Does anybody have the time? Is it 2:48? Can I do this in 2 minutes? Probably not. I think have I kept you over like 2 minutes at some point? I don't want to cheat you out of your tuition dollars. So everybody's gonna complain if I quit 2 minutes early. I think maybe I will just, the first one I might be able to do, but I think instead of rushing it, that'll be a nice warm up next Tuesday. So take 5 days to kind of take a breath here. I'll call it good at this point and let you guys go for today. Thank you so much for being here and stay safe out there in the rainy weather. You're driving around and I'll be around for office hours. If people want to get some help with anything or talk about anything, feel free to do that. Have a nice weekend.
Well, what is that says?
I'll email you guys the PDF with the solution today. Yes. Yep. Hey, thank you. That's tomorrow, isn't it?
Sure is.
All right.
How was